postdoc and then proceeded on to be associate professor. He specializes in geohydrology, permafrost, and physical properties of permafrost. And his talk today is near in line with a lot of my interests: permafrost remote sensing and using geophysics, airborne EM surveys, and thermal anomalies. And with that, I'd like to turn it over to Ronnie.
Thank you very much. Yeah, my name is Ronald Donnan. Let me see if I can start this and share this. Right. Do you guys see the right screen?
Yeah, it looks fine.
Yep.
Okay. Well, so this is the title of my talk. This is a study we have started now 2 years ago. It's funded by the National Science Foundation, or part of it. And some parts are from another project that is from, it's about Pilgrim Hot Springs. Pilgrim Hot Springs is also in an area with permafrost and no permafrost. And both areas were covered with airborne electromagnetic geophysics. And I'm just going over the data collection, how it looks like, and our goals with the collected data to understand more about the permafrost in those areas. So first, a little bit about the methods. So you see here a collage of methods. They're basically divided into two for the airborne EM. One is the time domain, the big loops you're seeing, and the other one is frequency domain. And it can be something that looks something like a torpedo that you drag through the air on a helicopter to a fixed wing with a funny loop around it. And so these are fairly substantial systems, not something that everybody has in their backyard. But there are plenty of contractors that are willing to step up the plate if enough money is spent. And so we decided to go with a frequency domain, actually in both cases, because it had a better performance in the near surface, and resolution-wise, it just came out better. Plus, the contract was a little bit cheaper.
Ronald, I just want to let you know that you're in the presenter mode where we can see the next slide.
That was my question. Yeah, okay. Let me try to fix that. I don't know why it switched to the other screen. Let's try that again. How do I change it? I think it's still the same right now. I have no idea. Yeah, you still see the wrong one, right?
Yeah.
Let's see. I think if I do this, then I go back. Share screen. This one. Now it should work.
Yep, that looks good.
Good. All right, so a little bit about the background, actually what the method does. In this case, you see a slide that explains a little bit the background. I don't know too much about it. There are other geophysicists there online that know a lot better, like Andy. So basically what we are trying to figure out is how fast the electricity current runs in the ground. This current is a function of the material that is there, And the material determines how electrical conductive the material is. It changes the signal that you can receive with the coil above ground. So you get a signal, you push a signal into the ground that creates a current. That current sends a signal back out, and that can be received with the receiver. And this way, you don't have to touch the ground at all. You just send in that magnetic field, and you measure the response. That is that. Let's go over to Pilgrim Hot Springs. For those of you that don't know where that is, it's on Seward Peninsula, western Alaska. It's just north of the Kiklawik Mountains, and the USGS, led by Jonathan Glenn, did a resolve study in that area and tried to understand the geothermal system. And the image you see is from that area. You see large trees there in the background because this is in the geothermal anomaly, which, of course, most of the peninsula is permafrost underlain, and you don't see trees like that. And so the idea was to try to see the extent of the geothermal system, but you can also see the permafrost around it. So I had this idea to look at, so where are those areas with the particular resistivity, and how does that relate to where we think permafrost might be. And this, you can see in the image, highly resistive is red, low resistive is blue. So blue are those areas that are not frozen, and anything in between could be frozen or not frozen. In this case, it's a little bit reverse psychology because blue is supposed to be cold, but in this case it's warm, and the USGS didn't get that message yet, at least not Jonathan Glenn. Anyway, this is the area from an aerial view, and a student of mine did some analysis on what types of surfaces you can see in a GIS analysis, and he related the surface type with the resistivities and was able to correlate fairly well those areas that have likely permafrost and is cold, and those areas that are a lot warmer. And the permafrost area, so Vladimir has a station somewhere in this region, somewhere here, fairly cold permafrost, mainly because the amount of snow that the site gets is blown off frequently, and all that snow ends up in big deposits around the trees, and then it melts because around the trees it's warm. There's a lot of heat coming out of the ground, and you can see that in this image. This is the hot springs themselves. You see in the image here, there are some houses. This is the old mission. This is actually a church that used to be all heated by the hot springs. And there's a pool right in front of the church there where people went for bathing. And if you take that period of time in a normal image, you see on the right here, the snowmelt areas of these hot meadows. And what's really beautiful, if you go there in spring, if you ever get a chance to, there is an enormous amount of needle ice that forms in these ponds because the surface is super cold from the atmosphere, and just a meter below it's 20 degrees plus Celsius. And so you have a very strong gradient, and there's lots of water there. Even though it is sandy soil, you still form a lot of needle ice, which is really fascinating. Okay, so that was just a short, simple study. We go to Goldstream Valley, is where we, a year and a half ago now, flew the resolve system in the entire watershed. The goal of this study is to understand where permafrost is and how it interacts with the groundwater system, and ultimately how it determines groundwater movement change as permafrost changes, and in relation to that, the carbon. So Katie Walter is involved with this study. We're looking at lakes in the area that are producing a lot of methane, and how does, so the question is, how does this bottom of permafrost and groundwater systems interact to create this methane flux? And as you can see, we have a fairly dense pattern from 200-meter lines to 100-meter lines in the areas of interest. And we followed creeks as a separate line just to be sure we capture that area well. This is an GIS view, 3D view of that same area, with some of the data collection points in there that were of interest. An interesting aspect of the groundwater is that most of the valley is potentially underlain by artesian groundwater, and so some areas might have artesian flow in private wells, and some people have had problems with that. They tried to keep an artesian well flowing, and then it started flowing out of control, and they couldn't stop it because they had to bring in liquid nitrogen to stop that flow. And so it is a very dynamic system and a very complex system. So if you let the result do its job, you will get back these images, and this is basically the raw image, various different frequencies, and the apparent resistivity that matches each frequency. Now, each frequency is sensitive to a different depth, and so you can have, roughly, you can say that the higher frequency, the shallower the depth. And so you can kind of make up your mind, but there is still, in the raw product, as you see it here, a lot of error that needs to be cleaned up. And so in order to do a better job with depth assessment, you do what's called an inversion of that data. And so you mill it through a computer system to create something like this. This particular model was created by EM1DFM. It's a product from the USGS, and as you can see, the color scheme didn't change very much, but now we have a particular depth. So this is 0 to 5 meters. What can also be seen is that there are still a lot of areas with noise. And as you can see on the corner of the slide here, this is the Fort Knox gold mine, and they happen to have a power supply line that runs right through our watershed, and it's a particularly noisy power line that creates these areas of funny data. Here's a different depth slice, probably more associated with where permafrost should be, around 10 to 30 meters. And you can see it's very blue. All the blue areas here are high resistivity. I don't say that they are all permafrost, but there's a lot of permafrost in this valley, particularly here in the bottom of the valley. And some of those north-facing slopes you can see there. But some of those south-facing slopes have actually talix and a lot of water in them. And in this particular case here, we see a lot of alpha ice forming during the winter. Now, this is a product from Workbench. It's a Danish code. It's a different way of interpolating the various frequencies. In this case, it is interpolating it in 2.5D, not quite 3D, but it's a little bit better. It uses information between lines as well as the information in a line. And these are resistivities again. So reddish areas are those areas that are less likely to have permafrost, and the bluish areas are likely to have permafrost. I'm pretty careful with my statement there because we see permafrost in areas that are fairly low in resistivity down to 100. And there you find degrading ice wedges often. So we are still in the process of trying to understand all that. So what kind of data do we have? Obviously, we have aerial photography from various slices. 1949 comes in mind. A lot of the lakes in the watershed, they didn't even exist back then. There is an old map from Peway that shows boreholes and areas of permafrost here. It's in pink, and areas of bedrock and silt. And if you overlay the resistivity, in this case the EM1 DFM, you kind of see a little bit the resemblance, but you also immediately see the complication. The bedrock seems to be very resistive, and there are areas, particularly these areas, that seem to be permafrost free, and they sometimes overlap with the Peway map, and sometimes it does not. And so there's still a lot of work to be done. There's what elevation, south facing, north facing, really means no permafrost and what means permafrost. And oh yeah, there was a line, I took that out of the slide. Okay, so other information we have, this vegetation. Vegetation is an important indicator, but it's also not the ultimate indicator of permafrost. Geology, this goes back into, where's the bedrock, how deep is it, what kind of bedrock. Bedrock typically resistive, but sometimes it is more conductive, so we need to tease that apart. Oh, and the other thing is fault lines, in this case, the pink lines, pretty active area. We have a whole suite of boreholes. These are DNR boreholes that report a variety of properties of the subsoil. In this case, silt is a very typical top layer and is reported in many boreholes. But the reporting is not very rigorous, and so you get things like brown mud and what was one of the other ones, shale, which is not supposed to be in the valley. So there are things in there that drillers just write down that don't always make sense. These are wells that have gravel. I think that makes a little bit sense. So the silt is typically underlain by gravel, and that's underlain by schist. And so you find the gravels mainly in the center of the valley, in the deeper locations. And these holes are mainly Peway boreholes from the 50s. And so here, who reported schist? Well, as soon as you get into the hills, there's a lot of schist. And if you drill deep enough, you get into the schist, typically in all areas. And these are wells that reported seeing frozen ground. So there are not too many, but, and this is still augmented with some wells we have from the DOT that drilled along the various roads in the area. The other thing we have is ground-based geophysics, and Andy is right there looking at his wonderful machine, and image of an OMapper person, Kevin Biela actually, and Tom Douglas, they were involved with doing some more OMapping in the valley, and that's the OMapper. So we have that to compare with. Vladimir put together these numbers. So we have temperatures to figure out where permafrost might be, very much related to topography. So that's good. And a little bit related also to this vegetation. And you see here some numbers. So we have in red is the air temperature, the mean annual. The ground surface temperature is in a greenish bluish, and the dark blue is the ground temperature And as Vladimir points out, in this case, there are still some questions in the valley as to whether there might be areas with talc and they're still covered with permafrost deeper down or not. And these are the kind of questions we are still trying to answer. And so if we, I'm not sure why it doesn't go forward. There we go. So we can use models. This is a very simple model idea that I tried to see what will happen. So this is a two-dimensional model with a mean annual air temperature and of -1 degrees, and you run that for a while, and then this is how it looks like. The colors represent temperature, and the black line here represents the freezing front, and the blue line represents an area of groundwater movement. So this is a typical scenario for the valley. Water is able to infiltrate near the top. It's coming up in the bottom somewhere. And of course, this is super simple. In reality, it's much, much more complicated, but just an exercise to see what modeling can do for us. So if you make the model a little bit more complicated, you allow it to vary temperatures between summer and winter, have some N factors, and to correct for this vegetation, it looks already a little bit more realistic. So you have your a lot warmer uplands, but still deep frost because it's very dry, and you have much deeper permafrost in the valley. And keep in mind, this model does not have any local inversion. These valleys have a pretty strong inversion. It's a lot colder in the valley than it is near the top. But you see that this development continues. Next slide. So if you let this run for 300 years, the frozen areas tend to go deeper to about 36 meters in this case. And there where groundwater may come up, it probably is not so deep. And we do see in the resistivity, for instance, that around the stream, Gold Stream, the permafrost is a lot more conductive, less resistive. And so, I mean, it does say something, but we also know that permafrost depths typically go down to 70 meters. That was measured by Pewee. That was the deepest permafrost measured in the valley. And so there's quite a difference between 36 meters and 70 meters, which could be attributed to the fact that there was no groundwater flow at the time the permafrost formed, or maybe the climate was colder, or probably both was happening. So yeah, this is just one exercise. We will do many more of these with a different model. This was done in COMSOL multiphysics. We'll probably use WASM to do some more of these measurements in the future. So one of the questions was the bottom of permafrost, and this is just a subset of the data set. You can see resistivities from very shallow to pretty deep, and 100 meters in the blue areas is pretty realistic, but in the red areas it's not realistic. So the modeling exercise overestimates the ability of the resolve system here. And typically my colleague Abraham cuts that out, but this was a preliminary product. He didn't cut it out yet. But where's the bottom of permafrost? I mean, you can't really say because it is resistive in many of these places throughout the column. And so you could look at the gradient of resistivity. And so again, shallow, and this is two differences. So it's a gradient between those depths. And once you get down to here, where we expect the bottom of permafrost to be, well, suddenly there are a lot of areas that light up dark red. So maybe this is a good indicator of trying to find where the bottom of permafrost might be in the valley. So to to go on with this resistivity and to determine frozen versus non-frozen, we really need to develop this geological model first. So we need to know how thick the silt is, where the gravel is, and where the bedrock is. And so this is just the first attempt at trying to come up with a three-dimensional model for the silt. You can see in there various points where observations were made in wells, and this particular model is still not very good, but it was a first attempt at trying to get to this. Okay, then, so what's left to do? So we really need to work on this geological model. It probably is the most important thing going forward. And we chose a modeling environment called 3D GoCAD, and it's used in the industry quite a bit to develop geological models, for mining, etc. Then we need to do the kriging. We decided to go to 3D kriging within 3D GoCAD in order to figure out what the resistivities are in the particular locations where we have well data. And so this is a process that is currently ongoing. We have a staff member putting in all that data into GoCAD right now. And hopefully we will get that geological model fairly quick, and the 3D integrated resistivities. And so we can start making a better guess at what areas are frozen, what areas are not frozen. I think thermal modeling will be a big part of trying to identify the boundaries of frozen versus unfrozen. And then we will come up in a few years with a 3D permafrost model of Goldstream Valley. Okay, and that was all I had. Thank you very much. Questions?
Awesome. Thanks, Ronnie. That was great. If anyone has questions, please go now.
I have a question. I'm not sure if you mentioned this, but how much does it matter whether it's ice-rich or not so ice-rich permafrost, your resistivity measurements?
Yeah, it's still a little bit of an open question. The system captures very much the bulk of the permafrost. So we hope it does something like 30 meters, but I think it's almost pushing it. So at 30-meter scale, you can imagine that if you have a network of ice wedge polygons, you may actually have conductors that bypass the ice. And so I think we see areas where we have only 100 ohm meters of resistivity, but still we see evidence of ice wedge degradation. And so we need to figure out how we can justify that. And then we do also have areas where the resistivity goes beyond 10,000 ohm meters, where I'm wondering about if that could be ice, and this is in the valley, it's in the bottom, so it should be relatively wet. So some of those areas I think we will be able to identify in terms of ice content, but other areas it will be harder.
So you showed your preliminary results from modeling the depth of silt layer throughout the Goldstream Valley, and I'm curious how much effort you think it might take to really refine that model such that it does well, not just for the Goldstream Valley, but perhaps more of interior Alaska, since superficial geologic information is so often not of the precision or accuracy that you want. Something like that I think would be a really neat thing to be able to.
Yeah, so I think there is a fairly strong relationship between topography and the silt layer thickness, and that's what I started using in my preliminary model. I think we also need to keep in mind the source area, which is typically, well, in this area, it's the Tanana River glaciers that we treated. That might change that distribution slightly. We again, we're not quite there yet. I mean, I had a discussion yesterday with Katie, and she said, well, isn't the silt a lot thicker on the toe of the slopes than in the center of the valley? Yeah, that might be so. And one of the things is transport by the creeks. So we know that the water movement is a big change on the landscape for silt accumulation and silt transport. So yeah, ultimately, you know, we come up with a set of rules, and we probably you can apply that to other areas. Any other questions?
Hi, this is Mark Waldrop. I'm just out of curiosity's sake, I'm wondering why did you start with the Goldstream Valley, and were you planning on doing continuing this in other locations where you don't have such old deep permafrost, you know, to the other directions out of Fairbanks and down the Tanana and so forth?
Katie was working in the Goldstream Valley on the lakes, on the methane fluxes, and we thought it would be easier to be close to Fairbanks. But yeah, other areas are interesting as well. There's a clear focus on permafrost, and you know, there's a lot of knowledge on permafrost north of Fairbanks. We can definitely expand. It's expensive to do this, so yeah, I guess that's all I can say about that.
Yeah, I guess I'll have a follow-up to that. So who within the USGS you said that there was like a USGS product that helped to create that electrical resistivity map?
Sorry, Burke Minsley helped us tremendously with the
electrical
first
resistivity.
EM1DFM. He'd actually developed that product. And
was that aerial? Was that something that was flown over it, or?
No, that's just a numerical model. The flying was done by a Canadian company, CGG or CCG. I never remember which one it is. Mm-hmm. They came out and used the Resolve product to come up with the data.
Cool.
And the other person, Jonathan Glenn, is the one who organized the resistivity data over Pilgrim Hot Springs. But there's, yeah, we have tried to get our hands on that particular product for some time now, and it does not seem to want to be released by somebody who paid for it. Yeah, so that's a little bit complicated right now. That's why we couldn't do more work on that particular data set. I think it's really interesting because we have now some temperature data, and we have a better idea of where the geothermal is and how it might affect the permafrost throughout that valley.
I'll just continue throwing out questions if it's
sure. Go ahead.
So when you look at that map, can you actually see the deep lakes or the shallow lakes or the? I mean, you could see some like the river bottom and so forth, but could you see individual lakes or bogs or anything like that?
Yeah, if the lakes are big enough, you can definitely see. So we are working towards an area called Big Lake right now, where we want to continue with some more detailed studies, flux tower potentially on the lake. And this particular lake wasn't there in 1949. And so we know it is a fairly young lake. It was a wetland before. And so there is some real degradation going on there over the last 50 or so years. And it shows in the resistivity that there is still some potentially frozen material down there. And the thaw bulb didn't quite make it through. but it's a little bit questionable because the lake levels seem to behave differently as expected with a closed bulb. But then again, there's also some beaver activity in the area that manipulates that water level, so it's kind of hard to say.
I guess I'm just curious as to how deep you actually see an influence of the lake or anything else.
Yeah, so that changes. So the depth of investigation changes with the resistivity. So that means that if you are in a cold permafrost setting, it can see beyond 100 meters. But as soon as you have a larger lake in that area, that depth is decreasing. And in the case of Pilgrim Hot Springs, you're dealing with salt contents of, what was it, 3,500 milligrams per liter in these geothermal liquids, and the depth of investigation plummets down to maybe something like 10 meters. So yeah, that's kind of the downside of the resolve system a little bit. If you have a time domain loop, like the large loop you saw in the beginning, they could go deeper than that if you specifically ask for it. So they come with a particular system that can see deeper in those scenarios.
Can I ask another question? I was curious how much the time of year matters when you do those measurements.
Well, that is a very good follow-up question, because we decided that we want to see as deep as we can, even in those areas that are potentially with talc or unfrozen. And to do that is to increase that resistivity near the surface, is to try to capture the landscape as it's coldest. And in this case, it's around February, March. And we were pretty lucky with the timing. We needed a good weather window to fly this, and we had 2 weeks of nice weather. And it was just 3 weeks before that a lot of the active layers in the area actually refroze. And so yeah, you want to try to capture the deepest points. Then springtime is the best time to fly this. And if you're interested in active layer depth, which this system cannot do, but if you're interested in other aspects of surface resistivity, then you would try another time of year.
I'm curious if you've had much interaction with the community. This is kind of a neat example where your research area is heavily populated, and it seems to me there's potential for a lot of people to be really interested, because it's going to help them learn about their property, what the hydrology is like, whether or not their wells likely to stay viable, all sorts of different things. And I'm wondering if you get much interest or maybe even some resistance from people in the community who maybe aren't familiar.
Yeah, that's a very interesting question. And so we had quite a few community meetings, and Vladimir is part of this study, and he was there. He actually lives in the valley. But there was a lot of chatter on Facebook in particular on us flying the area. A lot of the people in the valley are very smart. A lot of them are working at the university, and they know exactly what's going on. But yeah, there's some conspiracy theories of trying to read your mind with this banana in the air. And people were coming up with tin foil hats. There were pictures floating around about that. But in general, it is people that come there, they want to help out. So we asked them to measure snow depth. We asked them to report anything related to groundwater. You know, is there water spewing out of the road? And I know there's one person that is convinced there is a fault going through her driveway, and she's a geologist, so she should know. And she is reporting whenever there's water coming out of that fault line and running over her driveway. We have erosion issues going on in the valley, and Vladimir gets called out regularly to look at these sinkholes, and I was with him at one of these events just a couple of weeks ago, and we tried to, to look at the situation. Does it get worse over time? We tried to do our best in explaining it, and I also have a little handheld tool right now with VLF that does a very similar job to the Airborne survey, and unfortunately I can not see ice wedges with it. I tried to do that, but it didn't work. But yeah, so there is a lot of interest and from the residents, and we try to do our best to accommodate everybody. And yeah, there was one last thing. There was a hydrological study which is part of this as well. So we're looking at stream flow, and last winter there was an area that flooded and somebody reported it, and they also, and somebody else had reported that we were doing tests in that same creek just upstream of it. And then the rumor got out that, okay, we were the ones that caused the flooding. And of course that was not the case. But yeah, we did drill a hole in the ice and it started gushing water up through the ice. And so Anna Lildahl, the PI on the project, is actually went out there because she heard about this. He was not there when it happened, and she plugged it up with a log, and to make sure that there is no more question of us affecting the neighborhood.
Yeah, there's always going to be something like that.
Yeah.
But in the bigger sense that it's such a fantastic opportunity for people to see firsthand what some of the real tangible and immediate benefits are of cutting edge science like this.